Hi, Zach. Welcome to lesson number 73. This one starts on page 298. Whew, we're almost 300 pages into this math book. That's awesome. Whew, that's really cool. I better go ahead and order the next one pretty soon. All right, so what we are going to learn about today is way better than last time's lesson, like yesterday's lesson. I guess that would be for you. I don't make these every single day. So anyway, this one's going to be a lot easier and a lot more straightforward. Last time was long. Sorry about that. And it was about pyramids and cones, which to me, maybe you liked it because it's a lot of three-dimensional stuff. But for me, it's not the most straightforward thing in the world. So this one, I think you're going to like it a lot better because this is factoring the difference of two squares. And you'll see what I mean by that. It's going to be super easy for you because you are, like I said, a wizard at factoring. Okay, and then we're going to do a little bit of probability without replacement. Now, I do love probability questions, so those are going to be super fun. All right, let's start out with this comic. The livestock would gather every morning, hoping for one of Farmer Dan's popular airplane rides. Look at what he's doing. He's giving them airplane rides. And it sounds like the animals love it. So that's pretty cool. Okay. The difference of two squares. No, silly, not squares like that. Well, a little bit squares like that. But we're going to talk about factoring the difference of two squares. So this is actually really cool. Okay, so what we're going to do is instead of the typical trinomial, so remember the trinomial kind of looks like x squared minus like 2x minus 3 or something like that, right? That's a trinomial, has three different terms. But what if there's only two terms? Okay, and then let's look carefully at these two terms and you'll see what they mean by squared. So if you have a square that has a side of x and a side of x, the area is x squared. So that's what they mean by a perfect square. Same with this y. If you have a perfect square, you've got a y here and a y here, and to find the area, it's y squared. So this is a binomial, and each term is a perfect square. What about this one? This is also a binomial, and each term is a perfect square. So like if this is the area of a square, what would the sides be? The sides would be 2p, because 2p times 2p is 4p squared, right? So that's what they mean by a perfect square. So if 25 was the area of a square, what would each side be? It would be 5 and 5. So it's a perfect square as well. Okay, now let's look at this last term. M squared minus 16. So this is also two perfect squares, because if m squared is the area, each side is m. If 16 is the area, each side is going to be 4 and 4, right? Okay, so that makes sense. All of these three terms right here, or three expressions, are binomials, and it's a perfect square, and it's a minus sign. So it's the difference of two squares. So that's why I put this here. When you have the difference of two squares, then you do something special. Okay, this is going to be so fun. It's kind of like a little shortcut. When you have the difference of two squares, it's a super simple shortcut. And the shortcut is this. Oh, well, how do you even get the difference of two squares? I'm so glad that you asked. Of course, that's Willy Wonka saying that right there. They're made when you multiply the sum and the difference. Okay, I'm going to tell you the shortcut first, and then I'm going to explain why it works. Okay, so here is the binomial that we're going to factor. X squared minus y squared. So if we have to factor that, if they say on a test, factor x squared minus y squared, all you do is you make your two parentheses. Here's the shortcut. And you do x plus y and x minus y. Okay, and so whenever you do the difference of two squared, you do the sum on one of them, you do the difference on one of them, and then you basically take the square root of each thing. Okay, so the sum, the difference, and square root each term. Okay, so you might be thinking, well, how does that even work? Prove it, you might say. Alrighty, well then I will prove it. Let's prove it by taking the sum and the difference and foiling it out. All right, let's FOIL it out. See how it works. So if we were to FOIL this out, x plus y times x plus y times x minus y. Let's start with FOIL first. First, you have x squared, and then we're going to do outside x and y, and that's a negative y, so it's going to be minus xy. Then we're going to do inside x and y. So we're going to do, I'm going to write it underneath, plus xy, and then we're going to do last y and a negative y, and we square those, and it's going to be minus y squared. Oops, I should put that down. I don't know why I put it there. We should put it down here. Okay. Okay, minus y squared. So first, outside, there's the first. There's the outside, minus xy. There's the inside, plus xy. And there's the last, minus y squared. Okay, now remember, we add these together. And what happens to that middle term? You've got minus xy plus xy, and it turns into 0xy, which means you can just leave it out because 0 times anything, even if that thing is a variable, is 0. So it just turns into x squared minus y squared because the middle term always cancels out. Oh, let's prove it again because that was just so much fun. All right, so here's what we started with. This is the second term we looked at, 4p squared minus 25. Again, the difference of two perfect squares right there. Square minus square, so we can take the shortcut. The shortcut is take the square root of each one, 2p there, 2p here. The square root of this is 25 is 5, and you put a sum and then a difference. 2p plus 5, 2p minus 5. Okay, so that's the shortcut, but let's prove it, that when you multiply this out, you get this. All right, so we are going to do first 2p times 2p is going to be 4p squared. Let's do outside. 2p times negative 5 is going to be negative 10p. Now inside, 5 times positive 2p is going to be positive 10p. And now last is 5 times a negative 5, which is negative 25. Okay, let's add that all together. And we have 4p squared. Look what happens here. They cancel out again. Negative 10 plus 10 is 0p. 0 times anything is 0, so we can just leave that out. 4p minus 25. And bada bing, bada boom. Oh, it should be 4p squared. Yeah, that's what I said. 4p squared minus 25, and it's the same. Whoa, cool, huh? That was fun. So much fun that we're going to do it one more time. Yes, actually, you can even do it way more than one time, probably in your homework. So this is the last binomial that we looked at. Is it indeed the difference of two squares? Well, m squared, yeah, you can take the square root of that and just get m. What about 16? Yep, you can take the square root of that and get 4. So it is indeed the difference of two squares. So that would be m plus 4 and m minus 4. Do these, when we multiply them out, actually give us this? We shall find out in 60 seconds. That is, if we can finish that fast. Let's try it. First, m times m would be m squared. Outside, m times negative 4 would be minus 4m. Inside would be positive 4m. I have a feeling those are going to cancel out. And a 4 and a negative 4 is going to be negative 16. So let's add all that together. We get m squared. Negative 4m plus 4m is 0m. It's nothing. Minus 16, because I just brought that over. So m squared minus 16. Huh. And it's what we started with. It's like a magic trick, right? Super fun. So basically, what's the bottom line? The bottom line is if we are asked to factor a binomial that is the difference of two squares, square minus square, we are going to look just like him. We're going to look just like Luke. We're going to be like, no problemo, we got this. And what you do is if you have the difference of two squares like this, is you take the square root of each one, because it's kind of like saying 3m, that's the square root, squared, minus 7, which is the square root of this guy, squared. And so it's the difference of two squares. So what you would do, let me get a different color here. We would do 3m plus 7 and 3m minus 7. It doesn't really matter which one you do first. You could do minus and then plus first, doesn't matter. Okay, cool, right? So basically this is the general formula. If you have the difference of two squares, f squared minus s squared, you just do f minus s and f plus s. And notice that the f is the square root of that, and s is the square root of that term. Okay, cool, right? Okay, we're going to relax, and we're just going to do some examples, and we're going to make sure that we know this inside and out. All right, we're going to do example 73.1. That's on page 299. And here we go. The first thing to do is to recognize that this is actually the difference of two squares. Now, it's not a difference because you've got a plus sign, but don't let them fool you. This is easy to fix. How do we fix it? We do this. X squared minus 4. And you can do that because it was negative 4 plus x squared. You could just change it to x squared minus 4. And now what do you have? Now you have the difference of two squares. Because this is a square and this is a square. We just need to take the square root. So all we're going to do is I'm going to take the square root and do x minus 2 and x plus 2. Oh man, that was so easy. Way easier. Actually, in your book, they go through a different step. Let me just show you that really quick. And it's basically that step is to turn this into like x squared minus 2 squared. And then you just recognize that this square sign, when you get rid of that, you're left with this. Like when you take the square root of that, you're left with what's inside the parentheses. And then you take what's inside those parentheses and you do the difference and the sum of those things. But I think you can kind of do that in your head, so I won't make you do it. All right, example 73.2. Here we go. We're going to just keep swimming, just keep swimming. I know you're probably looking as annoyed as Marlon is there, but all right, here we go. We're going to factor the next one. 49m squared minus a squared, and the first thing that we do is we recognize that each of these terms is a perfect square. This only works with perfect squares. If it's not a perfect square, you can't do this little trick. And when it is, when you do recognize it, you realize that, can you take the square root of this guy? Yeah, sure you can. You can do 7m, and that would be squared, minus a, and that would be squared. Okay, so then, so they do this step. You don't have to do that step because I feel like I can do it in my head. But then you've got your two parentheses, and you do 7m minus a, 7m plus a. Easy peasy, right? All right, I love it. This is like a really cool shortcut. That was wonderful. Okay, I feel like Mr. Rogers here. Like, that was so fun. All right, let's do 73.3. They want us to factor this guy. Now look, this is actually a sum, and then there's a negative sign out here. So I'm going to do that little tricky trick that we did before and just change the order here. I'm going to do 25y squared minus 36a squared. Now I didn't change the problem at all. I just changed the order of those, but this is still a positive 25, and this is still a negative 36. It's still the difference of two squares. So once I change the order, I can realize it's the difference of two squares. I'll go ahead and do the step that they do in the book, but if you don't like it, you don't have to. I'm going to take the square root and do 5y, that whole thing squared, minus 6a, this whole thing squared. So do you see now how it's the difference between two squares? And then you can do 5y minus 6a times 5y plus 6a, and we factored it. Easy peasy. That was fun. All right, so you get the idea. You get it. Now we're going to move on to example 73.4. Oh, wait. No, this is not moving on. This is the same type of thing. Oh, it's just a little trickier. I didn't even recognize it as the difference of two squares because check it out. This looks like a very complicated problem, but you're probably thinking, you underestimate my power because you probably saw it right away. You probably saw it right away. It's still the difference of two squares. So let's rewrite it so it actually looks like the difference of two squares. 49a squared minus 36x to the 6th y to the 4th. Okay, I'm definitely going to, let's see, how do we take the difference of two squares? All right, so this is going to be 7a, the whole thing squared. And this is going to be 6, because that is the square root of this guy. What's the square root of x to the 6th? In other words, like x to what exponent, if you multiply it by itself, will be x to the 6th. And it turns out that it's half of that, because if you do x squared, because think about it backwards, if you're multiplying x cubed times x cubed, you're going to end up with x to the 6th. So this is actually the square root of that. Same with y to the 4th. What's it going to be? It's going to be y squared, because if I multiply y squared times y squared, I'm going to get y to the 4th, because you add the exponents. Okay, so then it's going to be that whole thing squared. So then difference of two squareds, I'm going to do 7a minus 6x cubed y squared, and then 7a plus 6x cubed y squared. Okay, there you go, difference of two squares. Now we are finally moving on. We're moving on to probability without replacement. Okay, so, well, I guess that's just a picture and not a GIF right there. Okay, that's all right. He's super excited about showing you this, so it's going to be fun. Basically, what we've been doing with probability problems is you draw a marble out of the urn, and then you put it back. And then you draw another marble out, and then you put it back. And it turns out that if you pull it out and you don't put it back, that's going to change the chances of what you get on the next draw. That makes sense, of course, because like if you pull out a white one and that one's not there anymore, then your odds are going to change over what's left, right? So here's the problem. An urn contains 3 black marbles and 5 white marbles. 3, 4, 5. Okay. A marble is drawn at random and then replaced. A second marble is randomly drawn. What is the probability that both marbles are black? So let's say you are super interested in getting black and then another black. Okay. So in other words, let's say you're on a game show and they've got this urn, but you can't see through it, and you have to randomly pick a marble, and the marble that you get is black. And if the second marble that you get is also black, maybe you win $1 million. So you really want to get black followed by black. Do you want to take the black out and leave it out? Or do you want to take the black out and then put it back in? I would say take it out and then put it back in, because if you take it out and you don't replace it, that's 1 black marble in there that's gone. And so there's only 2 left. Your chances go down of getting that second black marble, right? So let's see if we're right, because we're going to figure out the probability that both marbles are black. So what is the probability that we actually get black and black? And then for part B, we're going to say, what if it's not replaced? What if you take it out and you leave it out? Then what's the probability of getting black and then black? Okay, so let's figure out A first. The probability that both are black, and you pull one out and you replace it, and then you pull a second one out. Okay, so let's do that one first. So I'm going to move this out of the way. I'm going to move that down. What's the probability that both are black? So what are the chances of getting black the first time around? Well, you want a black one. It doesn't matter which black one you get. So there are 3 chances that it can be black. So that's going to be our numerator. On the bottom, it's the chance of getting any marble at all. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 marbles that you could get. So it's 8 on the bottom. Okay, so you pull out a black marble and then you put it back. And then you want another black marble. So to win the $1 million, right? So you have to do that again. So the chances of getting black the first time are 3 out of 8. What are our chances of getting it the second time? Well, the chances haven't changed because all the marbles are back in. So it's going to be 3 out of 8 again. And whenever you have to get 2 probabilities, 2 things have to happen, then you're multiplying those odds together. So your probability of getting 2 black marbles in a row are 3/8 times 3/8. And you know that when you are multiplying fractions, you just multiply straight across. So 3 times 3 is going to be 9. 8 times 8 is going to be 64. So isn't that interesting? Because out of 64 tries, you're only going to have that happen 9 times out of 64. Okay. Now, let's say this time for part B. Okay, so I'm going to erase this because that was the answer to part A. Now we want to do it for part B. So I'm going to move this up. Let's move this up. What is the probability if the first marble is not replaced? So the first marble is not replaced. What's the probability that both are black? So you pull a black marble out, but then you have to keep it. Okay, so we already did the first part of it. There are 3 black marbles. There are 8 marbles total. Now, for the second draw, we have pulled a black marble out and we had to keep it. So now this is what's left. Did you see me remove that marble? It's gone now. So this is what's left. So we have to figure out a new probability with that marble gone. So what are the chances of getting black? Well, now there's only 2 black marbles in there, so it's 2. And how many marbles are there total? 1, 2, 3, 4, 5, 6, 7. So times 2 out of 7. And when you multiply that straight across, 3 times 2 is 6. 8 times 7 is 56. Hi, Addie. What can I do for you?
Dad wanted me to tell you that dinner's ready.
Okay, dinner's ready. So we're going to finish this up pretty quickly. Now, 6 over 56 can be reduced, and you can reduce that fraction to 3 over 28, and that's the answer that they have in the book. Okay, cool. So which one's bigger, 3 out of 28 or 9 out of 64? Let's figure that out. Okay, I'm just going to get one easy way to do it is to just get your calculator out and just do, well, what is 3 divided by 28? And the odds of that are 0.107. What are the odds of, what was the other one? 9 out of 64. So 9 divided by 64 is equal to 0.14. So you do have a better chance of pulling out 2 marbles because this one's higher if you replace the black marble, and that makes sense because there's more black marbles to choose from. Okay, cool. Let's do example 73.6. All right, this is on page 300. Ding, ding, ding. I feel like we should get something for making it this far in math. This is the last example, okay, so pay lots of attention. Once again, an urn has 4 red marbles and 7 blue marbles. 2 marbles are drawn at random. What is the probability that the first is red and the second is blue if the marbles are drawn A, with replacement, or B, without replacement? So let's do it again. Let's start out with replacement. So what does that mean? That means that you draw out, you pull out a red one. Well, You pull it all the way to here. You pull out a red one, and you really want to get red and then blue. Now you're on a game show where they're like, if you pull a red and then you pull a blue marble, you will win $1 million. What are your chances of winning? Okay, well, first you pull out a red, and then you put it back, and then you pull out a blue. Okay, so let's figure out what are the chances of pulling out a red. So the chance of pulling out a red, let's count all the red ones. 1, 2, 3, 4. Your chances of getting a red are 4 out of all the marbles that could be there, right? So it could be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 4 out of 11 is your chance of getting the red in the first place. Okay, now you put the red back, and so the marbles haven't changed, and now you want your chances of getting a blue. So we're going to do times your chances of getting a blue, which are 1, 2, 3, 4, 5, 6, 7. So there are 7 blues, so that's a better chance of getting a blue. And then how many marbles total? Well, there's still 11 total because you didn't change the number of marbles. So it's going to be 4 over 11 times 7 over 11, which is 28 out of 121. Okay, so that's interesting because if you want to win $1 million and get a red and then a blue, your chances are 28 out of 121. It'll take 121 tries for you to get that to happen 28 times. So that's interesting. So do you want to do it with replacement or without replacement? I would say let's see, if you pull out a red and then you keep it out, I would say you would want to keep it out because then there's a higher chance you're going to get a blue the next time, right? Because there's one less red in there to confuse the issue. But let's see if that's true. So I'm going to erase all this because we figured that out. It's 28 over 121. Now, let's do it without replacement. In other words, you take it out and then you keep that one. All right, so let's try it. The chances of getting a red, we already figured that, is 4 out of 11. That doesn't change the first time around. But this time when you take the red out, you have to keep it out. So I'm going to erase one of the red marbles. Let's erase this one. Okay, so now what's your chances of getting a blue? Well, that's totally different odds because there's 1, 2, 3, 4, 5, 6, 7 blues. Should I do it in blue? Sure, why not? 7 blues. But how many marbles are there total when there's one gone? So instead of 11, there's going to be 10. Multiply that out, and your odds are 14 out of 55. So that is quite a bit better odds when you can keep the blue. So I would do that if I were trying to win $1 million with a red and then a blue. Okay, cool. And that's the end. Party time. You can go do your math now. All right, have fun doing your math, Zach. Love ya. Have a great day. Bye.